I'd like to welcome you to our event tonight, the PacWave Wave Energy Test Site off Newport, Oregon. I'm Colleen Kennedy, a volunteer with the Oregon section of ASME. Before we get started, I'd like to remind you that this event is being recorded so we can post-produce a video for our YouTube channel. You can go to YouTube and search for Oregon ASME to see all our videos. And now I'd like to introduce our speaker for tonight. Dan Hellin is the Deputy Director of PacWave, Wave Energy Test Site at Oregon State University College of Earth, Ocean, and Atmospheric Sciences. He's the Assistant Director of Test Operations of the Northwest National Marine Renewable Energy Center. This is one of 3 U.S. Department of Energy funded centers charged with facilitating the development of marine renewable energy technology. It's a partnership between Oregon State University, the University of Washington, and the University of Alaska Fairbanks. He has over 20 years of experience in coastal and ocean management, involved in numerous multidisciplinary research projects focused on a wide range of issues, including offshore renewable energy, marine spatial planning, port and harbor management, regulatory policy analysis development, waterfront planning. He has a bachelor's degree in zoology from Oxford, England, and a Master of Science in Tropical Coastal Management in Newcastle, England. His work has been in Bermuda, the University of Massachusetts, Boston, and now Corvallis, Oregon. Welcome to our ASME event tonight, Mr. Hellin.
Thanks, Colleen, and thank you everyone for joining this event this evening. As Colleen said, I'm going to be talking to you a little bit about PacWave, Wave Energy Test Facility based in, we're based in Corvallis. The facility itself is on the coast in Newport. So yeah, this evening, I'm just going to give a little overview of wave energy in general, an overview of PacWave as an organization, talk a little bit about PacWave South, which is our kind of grid-connected wave energy test site, the main part of our facility. Then I'm going to talk about some of the wave energy technology that we're hoping to see at our test site. And touch on some alternative uses or alternative applications of wave energy. So to start off with, why are we even talking about wave energy? Wave energy has a significant amount of potential. It's been estimated that the global energy market is going to be valued at about $700 billion by 2050. And it's also estimated that up to 10% of the worldwide demand for electricity could be met by harvesting energy from the ocean. So there's a lot of potential in marine energy and in wave energy in particular, because over 80% of this marine energy is estimated to be on the outer continental shelf, so slightly offshore, which would be wave energy. One of the nice things about wave energy as a renewable energy resource is that it's relatively constant, and increasingly waves are pretty predictable. There's been a lot of work done by people, including scientists and researchers at Oregon State University, to model waves and to be able to predict, what can be expected, 24 hours out. And that's of significant importance if wave energy is going to be part of the utility power generation. Also, wave energy is something that the US Department of Energy is very interested in. They're actively supporting the development of innovative technologies for harvesting energy from marine resources, including from waves. Oregon's kind of becoming the epicenter for wave energy in the US, and there's a number of reasons for this. One, if you've been to the coast, especially during wintertime, you'll realize that the wave energy resources off the coast of Oregon are significant, to say the least. There's also a robust electrical transmission system, which is important if you're producing electricity to go onto the utility grid. It's important that the transmission system is close to the source of where the power is being generated. Installing significant distance of transmission lines is an expensive undertaking. Oregon also has a really good transportation system and a series of excellent ports with great infrastructure up and down the coast. Also critically important is that there's an established and experienced marine industry within the state, from the fishing industry to the shipyards up in Portland. So there's a lot of marine industry itself and the support industries that go along with that, which is critically important for developing a new industry like wave energy. Also, what's fantastic about Oregon is there's a high degree of support for the testing of wave energy. Not necessarily commercial applications of wave energy, but testing. There is support from community level all the way up through state government and up to our federal delegation. At a community level, we've worked incredibly closely with the Newport community and other communities, and with the fishing community, who actually selected the location of our test site. And we continue to work very closely with them. And I'm not exaggerating saying that if we didn't have their support, we wouldn't be where we are today. Another reason why Oregon's a great place for wave energy is the fact that there's leading research institutes here. And as a bit of a plug to Oregon State University, OSU's been involved in wave energy for probably 20 years, from developing technology to research on waves to research about lots of aspects associated with and in support of the wave energy industry. We also have a number of associated facilities that we work closely with and which support marine energy. We have the Wallace Energy Systems and Renewables facility, the WeSurf Lab, which works with energy systems integration. We have the Hinsdale Wave Research Lab here in Corvallis, which, if you haven't had an opportunity to go there, it's an amazing facility. Has, I believe, the largest civilian flume in the country, and also has a large directional wave basin, which is also called the Tsunami Basin. A fantastic facility, a lot of work conducted there on coastal engineering, marine energy, all sorts of incredible work being undertaken at Hinsdale. We also have the Pacific Marine Energy Center, and that's not just Oregon State University, it's Oregon State University, University of Washington, and University of Alaska Fairbanks. And the focus there is really on the research, development, testing, and education associated with marine energy in general. PacWave used to be part of PMAC, and when we sort of moved into the testing phase that we're in now and soon to be operating a full-scale testing facility, we kind of spun out as a slightly separate organization to separate the kind of research and development and education piece from the pure sort of offering of testing facilities to clients, to people who are developing technology. The education, the student activity at Oregon State University is significant. These numbers are probably out of date now, but more than 75 PhD and master's students associated with marine energy, and many of them hired into the marine energy field or into supporting industries. Also hired by the national labs and academic institutions. So through the College of Engineering and other colleges within OSU, we have a great reputation of producing some fantastic students to sort of keep building this industry. On an industry level, OSU's been engaged with a lot of different projects through Hinsdale, through WeSurf, through PacWave, and through PMAC. So having OSU as part of the wave energy industry in Oregon is of great benefit, and is something that attracts industry people. So wave energy is still an up-and-coming industry. It's like a lot of new technologies, it's somewhat slow to develop. There's always hopes that it's going to take off, and things tend to work at a slightly different time frame. And there's a number of challenges which are not unique to this, not necessarily unique to this industry, but one is limited public and private investment into the marine energy industry. A critical problem is the limited testing infrastructure. As you're developing this technology, one of the critical things as you move through your development cycle, as you get close to that stage of commercialization, is to really be able to demonstrate your technology in the open ocean as close to the same situation as you would expect for when you go commercial. So grid connected, long deployments, multiple devices, and so on. And I'll talk about this a little bit later on, but there's very limited opportunities, limited facilities for testing devices. There's also, because it's a very new industry, there's a lack of technology convergence. There's a lot of different ideas and devices being developed, and as such, you know, at this time, no particular type of device has risen to the forefront of being the leading technology or the best technology. And this is one of the things, and I'll touch on this in a few minutes, but it's still, you know, there's several hundred, probably 250 developers out in the world at the moment with slightly different variations of technology. The costs and timeframes associated with developing any marine technology are high. The marine environment is very tough for technology, for testing, for developing new technology, and any deployment in the ocean is expensive. You're talking about deploying large devices. They need to survive out in the open ocean throughout the year, so through the winter when you've got extreme weather conditions. So you have large devices, you have heavy mooring systems, and then simply to handle the anchors associated with those and so on, you're talking about large specialized vessels which are expensive. So the costs associated with moving this industry forward are significant. There's also the fact that, you know, there's other forms of renewable energy that are, you know, very, very low cost now. Solar and wind, the costs have dropped. Wave energy is expensive, and with these other renewable energies in existence, the pressure to develop wave energy is slightly less. And then another factor which the industry runs into is the regulatory and environmental side of things. There are a lot of multiple federal and state agencies involved, and a lot of different regulations. And most of these regulations none of these regulations were written with the wave energy or marine energy industry in mind. Most were developed for oil and gas industry, have been adapted for offshore wind to a certain extent. So it's challenging when you have regulations that don't really fit what you're trying to do. And then there's the perceived environmental uncertainty. Because of the lack of testing, lack of steel in the water, lack of devices that have been deployed, there's some uncertainty surrounding the environmental effects. And a lot of those will be addressed once we can actually get devices in the water and conduct monitoring and research around those deployments to gather more information about potential environmental effects and hopefully put some of the uncertainties to bed. A lot of these challenges can be partly overcome by test facilities. Having steel in the water, running through the regulatory process with deployments, getting agency people up to speed and increasing the understanding of the marine energy industry, all of which is going to help the industry develop. And going back to what I said before, one of the key things is wave energy test sites, places where people can put their technology out in the water. And there are very few of them in the world. The leading one is EMEC, the European Marine Energy Centre, which is based in the Orkney Islands in Scotland. They have been involved in wave and tidal testing for probably 14 years. They're definitely the world's leaders at the moment, and they're part of our team developing our facility. There's a number of other facilities around the world. This probably isn't a comprehensive list, but as you'll see here, most of the facilities are based in Europe. The US, we have the Wave Energy Test Facility, or WETS, which is in Kaneohe Bay in Hawaii, off the US Marine Corps base. A great site, has some limitations to it. And then we have PacWave, which is really where the focus is going to be for most of what I'm talking about. This graph just shows the different countries, that the number of developers that come from different countries. This data is from EMEC, from the European Marine Energy Centre. They keep a database of developers. And as you can see, there's 250 plus developers in the world. A lot of them are in Europe, a decent number in the UK, but there's a significant number in the US. And this is part of the reason why there's an interest in developing increased testing capacity within the US. And I found this quote the other day. This is from Elaine Buck, who is a colleague and a friend from EMEC. And basically, it's just pointing out that while EMEC is the world-leading wave energy test facility at the moment, the waves in the Pacific Northwest are just so much more extreme than anything that Orkney experiences. And Elaine points out that basically testing and demonstrating technology off the coast of Oregon is a great location to be testing, because any technology that survives testing off Oregon pretty much survive being deployed anywhere in the world. So that brings us on to what PacWave is, and it's globally recognized open ocean wave energy test facility. The purpose is really to help clients, whether they're developers of the technology or utility companies who are looking to use the technology, giving them the opportunity to optimize WECs, wave energy converters as they're known, or arrays of devices as we move into commercialization of wave energy. People are going to be looking at wave farms, therefore deploying a single device is fine, but really what they need to be deploying is multiple devices. And we support that. PacWave allows that, multiple devices to be tested. A critical thing is proving the survivability or improving the survivability and reliability of these devices. If they're going to be out there for several years at a time, they need to be able to survive winter storms, extreme sea conditions. And part of the ability to operate in these conditions is being able to refine deployment, recovery, operation procedures, so that you're able to take advantage of weather windows, get out, conduct maintenance on these devices in an efficient manner, And part of what you need to be able to do that is practice with a test facility, near to a port where you can run through these procedures and tweak these procedures and improve these procedures. A critical piece for commercialization is to have a test facility that's grid connected so that devices are generating power. That power is being conditioned and fed onto the grid. And also a critical piece of PacWave is the environmental monitoring, the environmental research that's going to go on around devices, the effects of devices, and the economic and social benefits of wave energy. So PacWave consists of two sites. We have PacWave North, they're both located off Newport. We have Newport here. PacWave North is located about 2 miles off Yaquina Head, just north of Newport itself. This is a non-grid connected site. It's for sort of standalone testing of devices, generally smaller, possibly prototype devices, or other types of what are called maritime markets, other types of applications of marine energy, which again I'll touch on in a few minutes. PacWave South, which is the focus of my work, is currently in development. We've been working on the design and permitting for about a little over 7 years now. Soon going into construction, hopefully operational in 2022. And it will be a state-of-the-art grid-connected wave energy test facility. It will be, when it opens, the leading wave energy test site in the world. One of the things that's interesting with our site is it's going to be pre-permitted for most types of devices. And this is of significant interest to developers because it basically means they're not going to have to go through the full federal permitting process themselves to test at our site. We have gone through that process. They'll still have to provide a lot of the documentation to support their testing and safety procedures and environmental procedures and all the rest of it. But they won't actually have to go through what is a quite drawn out process to get their federal permits. The whole site is being developed in partnership with the US Department of Energy, also with the state of Oregon, local community, and with other public and private partnerships. So PacWave South itself is 2 square nautical miles. It's 2 nautical miles north-south, nautical mile east-west. It's on the outer continental shelf. It's 7 miles offshore. So it's in federal waters, not in state waters. The cables itself, as you can see, there's 5 cables running back to shore. The reason we have 5 cables is the test site is going to be divided into 4 test berths. So basically we have the opportunity, we have the capability of supporting 4 different technology developers, 4 different clients at a time. The total capacity of the site, we're going to be licensed for generating up to 20 megawatts of power and up to 20 devices deployed at any one time. The reason we have 5 cables is 1 per berth, and then we have an auxiliary cable, which is really a sort of largely going to be used for instrumentation, for research. It also acts as a spare cable for the site if need be. The reason you'll notice, rather than running straight to shore, the cable route runs down to the southeast, and this was because there's a rocky reef system between us and land, so the direct route to shore was not going to be a viable option, hence the route heading further south. The cables themselves, you may be able to see it just here where the mark is here, Close to shore, the cables are going to transition into 5,000-foot long conduits, which are going to be installed under the beach and under the nearshore system using horizontal directional drilling, each cable run into an individual conduit. The cables will then land at a shore landing facility, which I'll talk about in a second. And then another horizontal directional bore will run to what's called our utility connection and monitoring facility, where the power will be conditioned. Developers can monitor their device, can control their device, and then the power will go on to the Central Lincoln PUD's utility system. As I mentioned, we're in the design and permitting phase. We've been in that since about 2013, and we're moving into a construction phase, hopefully later this year, with the idea that we'll be open in 2022. This is just hopefully this will work. This is just a brief flyover showing where the technology is and the layout of the facility. So we start off flying out over Newport. We have OSU's Hatfield Marine Science Center here on the left. The ship operations here, the port of Newport just past on the right. Heading out through the jetties, heading out from Newport in a sort of southwesterly direction. The test site itself is about just under 10 miles from Newport. So for most vessels, you know, the normal vessels that we'll be using, you're talking about probably an hour transit time each way. We wanted somewhere relatively close to Newport to allow for a full day of work without having to stay on site overnight. As we come up on the test site, you'll see some yellow objects within the test site itself. These are, to scale, these are deployments of wave energy converters. So there's a cluster of 5 devices here, another cluster of 5 larger devices here, a third cluster here, and then a cluster of 5 devices here. And then we have the cables running back to shore. The cables are going to be buried in the seafloor. They'll be buried about 3 to 6 feet into the seafloor. We've conducted extensive geophysical and geotechnical surveys at the site and along the cable route to ensure burial. Partly this is to protect our cables, and 2, it's to prevent interfering with other ocean users such as fishing activity. As we get closer to shore, we start getting nearing the surf zone, the higher energy area of the ocean, and also areas that are rockier, making cable burial more difficult. And just here you transition into the light blue, which is the horizontal directional drilled bores coming out of Driftwood State Park, which is the cable landing site. And then the cable HDD bore running to our utility connection and monitoring facility. So as we just went past the site, you saw the deployment of the wave energy converters. This is the same layout as you were just looking at, with the cluster of 5 devices here, 5, 5, 5. But this shows the infrastructure that's below the water, in addition to the devices which you could see on the surface. So we have 3 cables in blue coming in at the north, a cable coming in, sorry, not at the north, that's actually the west, cable coming in at the south, and the auxiliary cable coming in on the east. The subsea cables themselves, these are 36 kV, three conductor AC cables. So they're going to be capable of supporting up to 5 megawatts per cable. That gives us the 20 megawatts per site. It's pretty substantial cable. The cables are probably about 4.5 inches in diameter. Each of the cables is over 10 miles in length. So they come in at a little over 300 tons each is what we're estimating. So cable installation is a significant technical undertaking. Each of the subsea cables is going to terminate in a subsea connector. We're looking at which specific connectors we're going to use, but this is one example. Basically, the connector is in two halves. One half of it will be on the end of our cable, and that will be provided by PacWave. And then the developers will provide the other half of the cable, other half of the connector to connect to mate to our half. And from their half of the connector, they will then have cables either running to the devices or to a single device or to a hub if they're testing more than one device. So that infrastructure from the subsea connector to the device will be for the developers to provide. Obviously, the devices themselves is their responsibility. And then the anchoring and mooring systems for each of the devices. And as I mentioned before, these are substantial devices and obviously have pretty substantial mooring systems. And these are a couple of pictures of the types of anchors that we expect to see on site. This is a drag embedment anchor, probably 20 tons or so. And this is a gravity anchor, and you can see there's 3 people here to give you some scale of the size of some of this infrastructure that will have to be deployed. As I mentioned, the cables are going to run back to shore. They're going to be buried. Cable laying itself, because of the handling of the cable, there's limitations to how it can be handled, the bend radius that it can sustain, and so on. So cable installation may be via a dedicated cable ship. That's still to be decided. That solicitation will be going out later this year for the cable manufacturing and installation. But it's possible it will be a dedicated cable ship, and that ship may have to come from Europe. The bottom picture is actually a jet plow, an example of a jet plow which would be used to actually bury the cables into the seafloor. Basically, it's dragged behind the cable ship. The cable's fed out from behind the ship through the jet plow, which cuts a furrow in the seafloor and lays the cable in as it moves along. The cables, as I mentioned, will then come and enter what's shown in here as purple, which is these 5 horizontal directional drilled bores. These will be stainless steel conduits running out 5,000 feet from Driftwood, breaking out, and we're hoping about 45, 50 feet of water. HDD operations you probably know about. This is a pretty significant operation. We're expecting that the HDD, the horizontal directional drilling at Driftwood, both the 5 bores out into the ocean and the bore back to the UCMF property, is probably going to take about 10 months of activity. We've just hired the company to do that work and are looking to start that work at the beginning of next year. The cable landing site itself is Driftwood Beach State Recreation Site, so it's a state park. There's a lot of reasons the state park is good. It's not too near to residences. It's a recreational state park, so while we're doing the work, we are going to pretty much take over and have to rebuild the parking lot. once we're finished. The HDD bores are going to be under the parking lot, under the dunes, under the beach. And then the yellow boxes you see are splice vaults, 10 foot by 10 foot by 10 foot, probably concrete vaults that will be set underneath below grade in the parking lot, where the subsea cables will transition to terrestrial cables. And this is some drawings of what the splice vaults might look like. We'd have a separate vault probably for each of the cables. They basically, the splice is made within the cables, and you have some spare cable in stored within there in case you need extra at a later date if there's a problem with any of the cables. As I said, these will be below grade, so when we're finished with finished our work in Driftwood, the parking lot will be rebuilt. They'll have a nice new parking lot. And apart from the manhole lids in the at grade in the parking lot, there should be no sign that we've actually been there. The final piece is the HDD bore from Driftwood down to the UCMF property. That's about 2,200 feet. There's a wetland area south of Driftwood, sensitive wetland. So we've done extensive geophysical and geotechnical work to ensure that we can have a good stable bore. The geotech that we've done has shown that there's siltstone from about 55 feet underground down to, we had a bore that went down 300 feet and we were still in the siltstone, which is great. It's a good material to get a good stable bore in. So we're looking at probably going down to a maximum depth of maybe 90, maybe 120 feet as we come from Driftwood down underneath the wetland, underneath Highway 101, and into our utility connection and monitoring facility. The UCMF, as we call it, is going to be a custom-built facility with the designs were done by HGE, an architectural firm based in Coos Bay. 3 buildings. The main building is this power conditioning building that you can see, and basically it would have a secured berth for each of the test clients where they can install their own equipment to monitor and condition the power. And then there's a control building where we'll have data and communication rooms, and then individual control rooms for each of the developers to monitor and control their devices. When a test is going on, the chances are that the developers will be there periodically, but most of it will probably be monitored and controlled remotely, whether that's from elsewhere in the US or elsewhere in the world. So the actual activity at the UCMF is probably going to be pretty limited on a day-to-day basis. So that's really the PacWave facility itself. I want to move now onto sort of what the technology is that we're looking to potentially have tested at PacWave. This is just a picture of some of the devices that are out there. As I said before, there hasn't really been the convergence of technology yet. There's still a lot of different ideas out there. This is again from EMEX data from February of this year. Different types of devices, and I'm not going to go through all of these, but I'll go through a number of them and just sort of talk a little bit about the technology. First, the first one at the top left, this is an oscillating wave surge device. This is generally deployed closer to shore, close to, if not in the surf zone. I just call it a flapper device. The picture in the middle at the top is Aquamarine Power's Oyster device. The picture on the right is Resolute Marine's device. Now you can see people in both of these pictures. They're very, very different scale devices. both of them deployed near shore. Actually, both of these devices pump water to shore rather than generate power themselves, and the power generation is done onshore through the pressurized water. Resolute Marine actually have a very interesting application. Their device, their technology has been developed largely to run reverse osmosis. So it's a small scale, easily deployable device. The idea is that it will be connected to two containers. One container, the water would be pumped into and would generate power, and the second container would contain desalination plant, a reverse osmosis unit. And their market is really looking for isolated areas without grid power where fresh water is a valuable resource. So it's a very interesting application of the technology and not looking at a utility scale application. The device on the type of device on the bottom is a submerged pressure differential. This is an interesting technology in that it has no surface expression. It's either bottom mounted or within the water, mounted within the water column. The two examples we have here, the middle device is an Australian company, Bombora. This is their M-Wave device. Basically, you have cells that get compressed by the waves, the pressure of the waves moving over the top of the device, forcing air through the ducting here, where there's a turbine mounted in the upper one of these ducts. So the air is circulated through that, generating power. They're about to do a deployment off Wales of a prototype device. The bottom right device is actually an Oregonian company. It's a company called M3 Wave. It's M3 because it was founded by three guys called Mike. They were all undergrad students at Oregon State University, and they have some interesting stories about how they came up with and did their initial proof of concept tests of their device, but I will leave that to them because this has been recorded, so I probably don't want to be telling their stories for them. This is, I believe, a third scale device. This is called the Apex device. And basically the white chambers have air-filled bladders, and as the wave moves over, it compresses the air in one bladder, forcing air through this tube here, which contains a bidirectional turbine, into the other chamber. As the wave passes over the other chamber, it forces the air back. This device was deployed 2 or 3 years ago off Warrington, off Camp Rylea, which is an Oregon military department base. They had it out there for a few weeks. Yeah, interesting device. The nice thing about the submerged pressure differential is no surface expression, therefore it doesn't really impact ocean users and so on, and it's also protected from extreme sea conditions. The next device is the point absorber, and this is normally, more like what people think as a wave energy device, a buoy bouncing on the surface attached to the seafloor. A lot of the technologies are point absorber technologies. The device in the middle is Ocean Power Technologies, OPT's Power Buoy. OPT were looking at deploying a number of these devices off Reedsport several years ago, but their plans changed. And then the device top right is a small scale prototype of Columbia Power Technologies, or Sea Power's Stingray device. Columbia Power Technology are actually based in Corvallis, and a number of their engineers came through the OSU engineering program. The bottom device is an attenuator device. The example that I have here is a device called the Pelamis. Pelamis have since gone out of business, but they were probably the most developed of the wave energy technology devices. It's a large device. This thing's probably 500 or 600 feet long. And the power is generated in the hydraulic articulation between the 4 separate units that you can see here. Couple more technologies. The top one is a horizontal pendulum device. This is an interesting type of technology. Both of the pictures that you see are 2 generations of a device called the Penguin by a company called Wello. I have no idea why it's called Penguin, but it is the Wello Penguin. The way this device works is that it's an inherently unstable hull, and then it has, as the type implies, a horizontal pendulum. So it's almost like a self-winding watch. The whole hull moves, the pendulum rotates and generates power. It's an interesting technology in that all the moving parts are inside the hull. So there's no external parts, which for deployment in the ocean is, is an interesting and clever approach to things. The bottom device is an oscillating water column. The sort of animated graphics is showing a shore-based facility, but the two devices shown, the middle one is ocean links. I don't believe they still exist. And the bottom right is ocean energy, and I'll talk a little bit more about them. The oscillating water column is an interesting type technology because it's basically the compression of an air-filled chamber within the device, and that air is then forced in and out through a turbine. So the turbine itself isn't in the ocean; it's being driven by air. And in these devices, you can see the turbines mounted above the device itself. This device in the bottom right, you can see the handrails. This is a small scale device just to give you some idea of the scale. This shows Ocean Energy's latest device. This is their OE35 oscillating water column device, which the picture, these are my colleagues in front of the device. It was built at Vigor Shipyard in Portland and completed last year. This thing's pretty enormous. It's 125 foot long, weighs over 800 tons. It's a joint venture between Ocean Energy, which is originally an Irish company. They now have a US subsidiary. And Siemens. Ocean Energy designed the buoy and built the buoy, and then Siemens provided the turbine, which is mounted up here, the gray turbine. The nice thing about this technology is you can upgrade the turbine. I think it's currently 500 kilowatts. The plan is, after the current testing, is to upgrade it to a 1 megawatt. As I said, this device was built in Portland. It was then towed to Hawaii, and the pictures of it in the ocean here at the dock in Pearl Harbor, awaiting deployment at the Wave Energy test site in Hawaii. It's an interesting device. The sheer size of it means it has survivability. You know, if it's moored correctly, if sea conditions get really high, they can simply allow the turbine to free spin, so not be generating power. These large openings here are where the water surges in, and then the air column is in the stack at the back here, forcing air out through the turbine. So it's an interesting technology. Hopefully it will be deployed maybe sometime this year, probably next year. This is just a little more information about the Wello Penguin device. Again, the same devices you said, same first and second generation devices you shown before. Wello's a Finnish company. Again, it's a large device, about 100 feet. It draws 23 feet. It's over 1,700 tons. You know, this is a heavy device. A lot of that is in the pendulum. 500 kilowatts. It's interesting, as I mentioned, no external moving parts. The first generation device, it was testing it, I think, between 2010 and 2019. It was deployed, I think, 4 times. I think the last deployment, I think, was 2 years. And they're now moving to deploy the next generation of device. And then this is core power. This looks much more like your standard wave energy devices, as a lot of people would sort of envision one. This is actually slightly clever in that it's a device with a single point mooring down to the seafloor. It's a tensioned mooring system, and the interesting thing about this device is it has phase control technology, so they can make it oscillate in resonance with the incoming waves. This is interesting for a couple of reasons. One, it increases its survivability in extreme sea conditions, but also they're claiming that they can get 5 times more energy per ton than other wave energy devices, which is interesting. It's also relatively small. The surface buoy's 26 feet in diameter, and the overall device is only 60 tons. So as far as maneuverability, shipping, handling is easier to do. Ultimately, they're looking at having clusters of devices generating up to 10 megawatts of power. But it's an interesting technology. The last one I'm going to cover, I'm basically just going to, if it works, just play a little video for you. Please tell me if the sound's not loud enough.
The WebTOS Wave Energy Converter delivers a stunning performance. With a high efficiency and optimized use of construction materials, WebTOS produces energy at a very low cost, making it a competitive contribution to global energy supply. Depending on the weather conditions, there is a great variation of energy from waves. WebTOS deals with this by changing the angle and the corresponding width of the wave energy converter. Therefore, the power to the generator is optimized to a much broader range of wave conditions, allowing a larger benefit to its annual energy production. The closing of angle in the system has also proven its superior effect in extreme weather conditions by minimizing forces on the structure. Without the need for extra strength to survive storms, costs are kept as low as possible. Access to WebTOS is safe through the calm area behind the wave energy converter, since the energy is removed from the waves. Inspection and maintenance can be carried out in a wide range of weather conditions. The WebTOS Wave Energy Converter is scalable and adaptable to all wave conditions. WebTOS technology is efficient enough to exploit the enormous resources in wave energy. This has been proven through extensive research and development. Coupled with its low cost, it will be an important contribution to tomorrow's growing need for energy.
So there's a couple of things about the WebTOS that I like. One of it is the ability to adjust the angle and therefore its ability to be able to withstand adverse sea conditions. It's a single point mooring like the core power device, and there's a few reasons why there's some benefits to a single point mooring, and they're largely from the environmental aspect. Fishermen prefer it because their gear is less likely to get tangled up on a single point mooring. And the resource agencies like it because the chances of entanglement of marine mammals and so on in the mooring systems for wave energy converters is pretty low because of the diameter of the lines and the fact that they're under tension. But what you can get is the risk of secondary entanglement if fishing gear gets entangled on it. So, single point moorings are good, the survivability aspect of being able to adjust the angle of the wet toss. But the one thing I really like from a practical standpoint is the fact that you get calmer water in behind it, because the maintenance of these devices is going to be a significant challenge at times, and having the ability to have some protection from the ocean, from the sea conditions when you're trying to get onto the device and undertake maintenance is actually critical. So anyway, they're from Denmark. They're continuing to develop their device. I think they're at a 1 megawatt device being tested at the moment. Ultimately, they're looking at about 4 megawatts. So, there's just scraping the surface of some of these technologies that exist. But, as I mentioned before, there hasn't been the sort of convergence of technologies yet. And a lot of these technologies are still very much in the development cycle and need to do this open ocean testing. And as I mentioned before, there's a limited number of facilities. So PacWave is really hoping to be the test site for the US, and also the entry point for European technology developers to come and show their technology, demonstrate their technology for the US market. Just to finish up, finally, just touching on a slightly different application of wave energy. So far, we've been focusing on the sort of utility scale application, but there's a whole other sort of industry, and sometimes called maritime markets. The Department of Energy talks about technology for powering the blue economy, but it's really the application of marine energy, which isn't a utility scale application. And these are just a few examples, and I'm not going to go into a huge amount of detail, but the first one is smaller scale, community scale applications of marine energy. And this is going to be probably where marine energy is first going to be applied. There's a lot of interest in places like Alaska, where you have communities that are running diesel generators for power. They'll have 4 generators, 2 generators running, 1 being repaired and 1 as backup. There are even some communities where the diesel is flowing in. So the cost of generating power is enormous. And the potential for wave energy or tidal energy, or as our colleagues at the University of Alaska Fairbanks are looking at, generating power from rivers, has huge potential for applications in communities like in Alaska or other communities that aren't on the grid. Desalination I touched on briefly with the Resolute Marine device. One area of interest is recharge stations for autonomous underwater vehicles. There's a lot of interest in using AUVs for inspection and maintenance for wind farms, wave farms, oil and gas. And the top illustration is showing the ocean power technology power buoy coupled with Saab CI, who this device here in the ocean is their saber-tooth AUV. And the idea is to have a docking station so these AUVs can be recharged and upload and download data. Similar type idea for powering oceanographic buoys. A lot of them have photovoltaic solar panels on for keeping them charged. There's no reason why they couldn't be using wave energy. And the last one I'm going to mention is offshore data centers. And it seems a very strange application, but this picture down here in the bottom right is Microsoft Natick was the project, and this was a data center that was submerged at EMEC, and as a test, as a prototype. But data centers require a lot of power and require a lot of cooling. So one of the ideas is generate the power from wave energy and use the ocean to cool them. I don't know how much this technology is going to take off, or this application of wave energy is going to take off, but I thought it was an interesting, novel application. So that's really all I have. As I said, we're looking to go into the construction phase this year and hopefully be operational phase in 2022. So our hope is that come 2022, some of these devices will be deployed off the coast of Newport. It's been a long process. We have a large team. Our team at OSU is actually pretty small, but we have a large number of consultants and partners, from the national labs to the Department of Energy itself, to a large number of utility companies and engineering companies who have all been part of this project and continue to be part of this project. So that's all I have, and my contact information is here. I'd be happy to answer questions, and if you have questions afterwards at a later date, feel free to email me, and I'll be happy to try and answer things. Thank you.
Well, I found that a very interesting survey of the maritime energy research and development happening here in Oregon. For those of you that don't know me, I'm Trevor Scheck. I'm the current chair of the Oregon section. I'd like to take this moment to say thanks to Dan for his wonderful talk tonight. Thank you, Dan, for your time and effort in preparing this presentation. I'd also like to thank you and your colleagues and your teams for your contribution to furthering new engineering technologies. As a leadership team member here in the Oregon section, I find myself privileged to engage with people such as yourself, and I look forward to seeing and reading more about the progress made at PacWave and in the marine energy industry in the coming years. You mentioned that the Pacific Northwest has some of the most energetic waves in the world. I'd also like to point out that we also have some of the most energetic volunteers within ASME. So on behalf of our Oregon section and the Pacific Northwest as a whole, I'd like to present you with a certificate of appreciation for your presentation tonight. Our AV guru and energetic volunteer, Pasquale Duaco, is showing it now virtually. Unfortunately, we can't give it to you in person, but certainly a PDF will be made available for you to print and put on your wall. So thank you so much.
Thanks very much indeed.